Okay, good morning. I hope that all of you are fine right now. We are going to continue uh, with a new topic right now, and I hope that we can finish this by today because we only have one more week to go. So this is a new topic. The topic is about recurrences. Yeah, what is a recurrence? Recurrence is something that recur, something that occur again and again. And we will see that this is actually exactly match with a sequence that we have already discussed last week. If last week we are talking about summation, then summation is when you sum all of the components of the sequence. Now, what we are talking about is not summing them up, but representing them, showing them, displaying them. But exactly, what do I mean by exactly? Well, if you have a sequence, you may list them. You may list all of the components, like I said last week. So you may list them if they are finitely long. For example, 1, 2, 3, 4, and then that's if that is the sequence, and that's enough. Now the problem is sometimes our sequence is infinitely long, and for this you use ellipses 1, 2, 3, 4, 5, and so on and so on. Like I said, uh, is is something basically that relies on on the reader, on the knowledge of the reader. Now recurrence allows us to represent this sequence exactly, to represent this sequence uh, without this ellipsis whatsoever, without the need to use ellipsis. Okay, you are going to look at this much more closely. Uh, by the way, yeah, I mean, can you hear me right now? Okay, let's continue then. Okay, now a recurrence basically describe a sequence of numbers. Usually in the beginning, we explicitly show a few terms, and then the next terms are expressed as a function. Look at this, as a function of the preceding terms, those that are already been explicitly shown, or a function of the other preceding terms. Yeah, let me show you a simple example. This is an example that describes the sequence of natural numbers. Yeah, so we basically specify that T1 is the first term, as equal to 1. T1 is equal to 1. So this is what I mean by explicitly shown. So we set that T1. So this one here can also be can also be regarded as the parameter of the function. So the function is T, and the parameter is 1. So T, when parameter is 1, is equal to 1. And then the rest will be described by this function. So Tn, T, when the parameter is n, is equal to Tn minus 1, T, when the parameter is n minus 1, plus 1, for all n larger or equal to 2. Look at this. So this is basically the core or the essence of recurrence. Why do we call it recurrence? Because the function occurs on the left side and on the right side of the equation. Yeah, so it occurs on the left side and on the right side of the equation. So this function basically is explained or is described by itself. The only thing, of course, that is that if you look at this is t when the parameter is n is equal to t when the parameter is n minus 1 plus 1. So the function at a particular time or at a particular parameter is described by itself at another setting of parameters. So that's why we call it recurrence, because the function recurs. Now, if you look at this function, then a function, of course, can be only a recurrence if it is diminishing. Look at this, diminishing. So if the parameters is smaller and smaller and smaller and smaller and smaller. If the parameter is larger and larger and larger, then this will be quite different, because if it is getting larger, then the final result will be infinity, basically. So we cannot use that. There is no meaning to that. So, but if the parameter is getting closer, getting smaller, then it must finish somehow. When does it finish? When does it finish? This is usually provided by the boundary condition. This is the boundary condition. Yeah, this is what we call the boundary condition, when it finishes. Okay, so this is an example of recurrence. Now, once we have this recurrence, what do we do? If you see, this recurrence actually described a sequence of natural numbers. If you see, the first number is equal to T1, which is equal to 1. What about the second number? The second number is easy. What you have to do is just replace this n by 2, and then consistently replace all of the n's by 2. So that means T2 will be equal to T2 minus 1 plus 1. And then you evaluate it. When you evaluate it, this will become T2 is equal to T1. T1 is equal to 1 plus 1, so T2 is equal to 2. And you can continue this. T3 will be equal to T3 minus 1 plus 1. Well, T2, previously you know that this is equal to 2, so T3 is equal to 3. And so on. You can, if you evaluate this again and again, you will find that this is basically this forms the sequence of natural numbers 1, 2, 3, 4, 5, 6, 7, and so on. But you don't need to say so on. That's the beauty of it. You don't need to say so on, because the so on is actually encoded in this formula. We don't have to know. You don't have to guess. Yeah, you don't. I mean, there is a guarantee that the formula is valid. That it describes basically the sequence. Okay, recurrence is a tool that you will use often later on, especially in analysis of the performance of recursive algorithms. What is a recursive algorithms? You will learn about this in other course. Yeah. So, but to form the recurrence is not enough. It is actually a good idea, a better idea, if once you form a recurrence, we can also solve it. What does it mean by solve it? Solving a recurrence means to find a closed form solution of the nth term. Well, sometimes, most of the time, we can find the closed form solution of the recurrence. That means that we can solve it. But actually, there are also recurrences that cannot be solved, namely, that does not have a closed form solution for its nth term. What does it mean by closed form solution of the nth term? So we have a formula that describe a simple formula without the function t that describe the nth component, the nth term. So that means that if you have this formula, if I ask you what is the 100th term, all you have to do is just replace the n by 100, and then voila, you have basically the number. Yeah. So there are two techniques that we can use to find the solution. The first one is called guess and verify. We'll see this later. And then the second one is plug and chug. Guess and verify basically relies on your guessing. If you can guess, then it's okay. We will be able to find the solution. But plug and chug, when the plug and chug does not rely on guessing, so basically this is a much more robust method. And then we will also show you two classes of recurrences. The first one is called linear recurrences, and the second one is called divide and conquer recurrences. And these two classes I mean, there are methods, basically different methods, distinct methods to solve these two classes. We will learn about this later. And then recurrence occurs naturally in computer science. If you see, in computer science, when you form an algorithm, usually what you do is to try to 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 make your problem smaller progressively. So if you have a big problem, then you solve this by usually uh, dividing it into smaller problems. And once it is small enough that you can basically you can conquer it, you can solve it in a simple way, then you proceed. In the end, you can basically solve the whole problem. This is similar to induction and recursive algorithm. Yeah, so this is very natural in computer science. This is basically what we are doing when we are designing an algorithm, and recurrence also shows this, basically displays this characteristic. Okay, let me show you the first example. This is a very famous example called the Towers of Hanoi. So your duty is like this. So there are basically n disk here on the first tower, and disk. So this disk has different radius, different radius. One, I mean, they are not of the same size. So we order them from the largest to the smallest. So the smallest is on the top. So what you have to do is to move all of this to the third tower. Yeah, to the third tower here. Yeah. So you have to move them. You have to move all of this to the third tower. But we have two requirements. So our goal is to move all, let's say n is equal to 64, disks from the first tower to another tower. Well, let's just say that the third towers, with these two rules. The first one, the only action that you have to use is to move one disk per one disk. You cannot move two disks at the same time. And of course, you cannot move this third disk because there is no way to move this. So the only thing that you are allowed to do is taking the topmost disk and then move it to another tower. Okay. And then, so you cannot basically take two of them, only one by one. And the second one, so in any configuration, a larger disk must be below a smaller disk. So you cannot, for example, move the smaller one to the second tower and then the next one also on top of this. This is not allowed. Yeah, this is not allowed. So a smaller disk must be on top, must be above a larger disk. Okay, so the problem is, how do we move it? Yeah, or at least basically what we are going to compute right now, how many steps do you need to move n disk from one tower to another? Let me show you an example. Assume, for example, n is equal to 3. So basically, when n is equal to 3, this is still small enough that we can cover them, that we can show how to do this basically one step by one step. Let's look at n is equal to 3. So this is the original configuration. And then I move the topmost, the smallest one to the middle. Sorry, to the third tower. So this is one step. This is what we mean by one step. You move one, this is one step. And then from this configuration, I move the middle one to the middle tower. So this is the final configuration. So this is the second move. The third move, I move the smallest one to the top, to the middle. You see? I move the smallest one to the middle. So this is the third move. And then I move the largest one from the first tower to the third tower. This is the fourth. And then I take the smallest one, I move it to the first tower. Okay, this is important because you cannot move the middle one right away to the third tower. You have to move this first. So this is the final the configuration. This is the fifth move. Yeah, and then I move the middle one on top of the largest one to the third tower, and then this is the sixth and the seventh completed. So the smallest one to the topmost. You see the idea right now, how to perform the moving and how many steps do we need. Okay, this is for n equal to 3. What about n is equal to 1? N is equal to 1 is okay. I mean, if there is only 1, so that you just have to move it to the third tower, that's it. 1 configuration is enough. What about 2? If it is 2, you just move the topmost one to the middle, move the other, the one below 2 to the third, and then afterward you move the middle from the middle to the third. So we need three steps. Okay. So how do we solve this in general? Well, you know this for basically a couple of things. You can try it, of course. You can try for n is equal to 1, 2, 3, 4. But we want to know the final solution of this for arbitrary n, for even for a large n. For example, n is equal to 64. So the way to solve this is we will denote this as a function. Take the function. We call this Tn. The function is T. Tn denotes the minimum steps required to solve this problem for n disk. So if you have n disk, Tn is basically the number of steps you need to move from the first to the third tower. Okay? So then, if this is the case, then Tn minus 1 will be the number of steps you need to solve this problem if you have n minus 1 disk. You see, so the idea is of the function is like that. So once you define it, then you can define it for any n that you like. Okay, so we can try. I mean, like I said before, like I described, we have already seen that T1 is equal to 1. So we know the boundary condition right now. T2 is equal to 3. T3 is equal to 7, I think, in the previous slide. Okay, so but how do we solve this for general? How do we solve this in general? Well, in general way, to solve this is to think abstractly. Pay attention to this. This is what we call thinking in an abstract way. Yeah, thinking in an abstract way. It is important to think of this in an abstract way because even though we don't really know the very detail, by thinking about this in an abstract way, we can actually deal with this in an easy way. So let's see. So what do we have to do if we want to move n disk from the first to the third towers? Well, all you have to do is actually like this. Take the first n minus 1 disk, the topmost n minus 1 disk from the first tower and move it to the middle tower. Of course, you cannot do this in one shot, but there must be a way to do this. It takes a lot of steps, but there must be a way to do this. So this is basically just pretend that the largest one, the bottommost disk here, does not exist. And then I ask you, move the n minus 1 disk from the first tower to the second tower. Now the question is, how many moves do you need? Well, I don't really know the detail of the moves, but I know that it must take minimum t n minus 1. You see, this is basically what I mean by thinking abstractly. We don't know the detail, but we know it must be t n minus 1. In principle, it must be t n minus 1 because that's the way we define the function. So all you have to do is move the first one, the topmost, the n minus 1 topmost to the middle. How many steps does it need? Tn minus 1. And then, if we have it, this is the configuration right now. Now, and then what do you have to do? Well, this is simple right now. All you have to do is to move the bottommost disk from the bottom here to the third tower. How many steps does it need? One step. You don't need any function for that. You need only one step. So this is the configuration right now. Now, once you have this configuration, what do you have to do? Well, the only thing left is to move all of this n-1 disk from the middle tower to the topmost here, to the top of the bottommost disk. Yeah. Again, of course, you cannot do this in one shot, but there must be a way to do this, which is very complicated, moving around and so forth. But there must be a way to do that. Now, the question is, how many steps do you need? Again, we don't know the detail, but this is easy. It's just simple. You just use the function, the knowledge of the function. It must take a minimum Tn-1. You see, I just think about this in an abstract way. Yeah. So thinking about it in an abstract way result in something really concrete. So let me back again one slide, and you could look at this. So this is basically what I have done. Move the topmost n-1 disk from the first tower to the second tower by using the solution that we know for n-1 disk. How many steps do we need for this? Tn-1. And then move the largest disk from the first tower to the third tower. How many moves do we need? Exactly one move. And then the third step, move the n-1 disk that you have already moved to the second tower, from the second tower to the third tower, by using the general solution for n-1 disk. How many moves do you need? Tn-1 move. So then, I will just skip this slide. So then, what do we have? What do we have is this one. Yeah? What we have is this one. So we have Tn-1, the first one. So let me return again here. This one for moving this one, we need Tn-1 plus 1, because we move this to this one, plus 1, plus again Tn-1. So the final result is 2 Tn-1 plus 1. So this is our recurrence. Our recurrence is Tn is equal to 2 Tn-1 plus 1. It is actually a better idea if you use function instead of this one. I know, but this slide is a little bit old. Because, if you want that later on to use a function, this is actually well help us to clarify things. So instead of doing a subscript like this, you just say t and then as a function. Sometimes we can see clearer that way. So what I mean is that instead of writing it like that, we can just write t n is equal to 2 t n-1 plus 1. See, if you use this function notation, I mean, you get the feeling right now. I mean, it becomes clearer. So we have a function here t with parameter n, and then this is equal to, because we need twice Tn-1 and plus 1. Okay, so let's return to the slide. We know this, the form of the recurrence. Every recurrence requires a boundary condition. This is the boundary condition. This is the boundary condition is basically the one that we know for sure, that we describe, express explicitly. We know that T1 is equal to 1. So when you have only one disk, then the number of steps that you need is equal to 1. So we know this in real life, so you just fix it. T1 is equal to 1. Yeah? Okay then. So that's it. That's basically, we have just learned how to convert a real life problem to becomes a recurrence problem. You see a real life problem and you convert this into a recurrence problem. A real life problem becomes a mathematical problem. So once it becomes a mathematical problem, then all you need to do is just to solve it, but then you have a lot of arsenal basically to do this. You have a lot of tools in mathematics that helps you to do this. So this is basically, this is actually more important than just knowing how to solve this mathematically, because the ability to transform it from a real life problem to a mathematical problem, this basically is called modeling, and this is much more useful for you later on. So how do we solve this? Well, if you want to solve this, you can try, of course. I mean, the easiest way to do this, try a couple of one, and you see pattern. For example, if T1 is equal to 1, then T2 is equal to twice T1 plus 1, so 2 multiplied by 1, 3. Then T3, it's around 7, T4 is 15, and so forth. And you see, if you try them, then for a couple of terms, a couple of first terms, then you find this sequence. The sequence is 1, 3, 7, 15, 31, 63, and so on. Okay, now let's continue. How do we solve this recurrence? How do we solve this and find, for example, number of steps that you need to move 64 disks? Yeah, of course, if I ask you to find the number of steps that you need for 64 disks, you can try it. You can compute it yourself, starting from T1 and then T2 and then T3 and so forth until T65. You can even program this in computer. This is easy, but it takes a long time because you have to do recursion basically. Yeah, because you have to do looping and then performing this computation manually. It takes time. Is there any closed form solution? Now, if you have a closed form solution, then the result will be a formula. All you need to do is to evaluate this formula. So let's see. One of the methods to solve this recurrence is called the guess and verify. From the name, we know that it requires guessing. Okay, so how do we guess? Well, let's see. If you see this by looking at this sequence, 1, 3, 7, 15, 31, 63, well, it looks like this 1, yeah, and then the second one is 3. This looks like 2 to the power of 1 minus 1, 2 to the power of 2 minus 1, 2 to the power of 3 minus 1, to the power of 4 minus 1, and so forth. And we can guess, oh, it looks like that the Tn, that the solution will be Tn is equal to 2n, 2 to the power of n minus 1. Of course, guessing is not enough. Once you guess it, you have to verify it. How do you verify it? How do you prove it? Yeah? How do you prove it? Well, this is basically our claim. This is our guess. Tn is equal to 2 to the power of n minus 1. And we claim that this satisfies this recurrence. How do you prove this? You can prove this by using induction. You already know induction in before the midterm exam. We can prove this by using induction. Let me show you the proof. Well, you just write, we prove this by using induction on n. What is the induction hypothesis? The induction hypothesis is that Tn is equal to 2 to the power of n minus 1. So let's see the base. The base. Well, the base is when n is equal to 1. So you try it. When n is equal to 1, plug it here, put it in this formula. So T1 will be 2 to the power of 1 minus 1, which is equal to 1, which is equal to the recurrence. The recurrence also say that T1 must be equal to 1. So this is okay. Let's continue with the induction step. Assume that Tn minus 1 is equal to 2 to the power of n minus 1 minus 1. How do I know this? Well, if you already accept this claim, then by replacing all occurrence of n by n minus 1, then this is right now becomes a fact. You see? Yeah. So if you already know that the hypothesis, that the induction hypothesis is equal to this one, and you accept this as a truth, then all you have to do is just replace n by n minus 1, and the whole thing will be just fine. And we have this. So this also then is a truth. Now we will show if we believe this one by using this claim, then we will show that Tn is equal to 2 to the power of n minus 1. So Tn is equal to, use this, use the recurrence, use this fact right now, because this is the only fact that we know. So Tn is equal to 2 times Tn minus 1 plus 1. What is Tn minus 1? Tn minus 1 is equal to this one. This is our assumption. If you believe this one, then this is basically also a truth in using our assumption. So 2 times 2 to the power of n minus 1 minus 1. Twice this one, look at this. Twice this one becomes 2 to the power of n. But there is also a catch here. This must be minus twice minus 2 and then plus 1. So the final result is 2 to the power of n minus 1. So we know this. So this is basically proved. We have already proved by using example that Tn is equal to 2 to the power of n minus 1. Okay, let's continue. Now this is what we call a guess and verify method. But like you see, I mean, in the beginning, we rely on basically on your ability to guess. What if the recurrence is so complicated that you cannot guess the form of the recurrence, the solution of the recurrence? Then you cannot do anything. So basically, this relies on you being able to guess. Yeah? So this is basically the major drawback of this method. Now, is there any other method? The other method is called plug and chug, and we will spend more time on this one because this basically allows you to solve any recurrence. Yeah. So the major disadvantage of the guess and verify method is that you have to correctly guess. If you correct wrongly, then you will not be able to prove it, and the whole thing will be, will be just endless. Yeah. So a plug and chug method is, we can use this if you are not able to guess. Now, actually, plug and chug also uses some sort of guessing, but we are guessing on a different level. We are guessing by looking at patterns. Yeah, the patterns. This will become clearer later on. So let's see. So there are 3 steps on this method, on this plug and chug, and then pay attention to this one. The first one. In plug and chug, take the main recurrence and perform plug and chug again and again and again. It may take a couple of iterations, a couple of times performing plug and chug until you are able to see a pattern, until a pattern basically arises. What does it mean? Well, let me show you right away. Look at this one by one. In the beginning, we have these original, you take the major, you take basically the main recurrence. This is the main recurrence basically. Tn is equal to 2 Tn minus 1 plus 1. This is the main. This one is called the boundary condition. Yeah. So take the main recurrence. Then this is it. So Tn is equal to 2 Tn minus 1 plus 1. Okay. You know this? What do we do next? Well, if you know Tn is equal to 2 Tn minus 1 plus 1, you are supposed to know also Tn minus 1. What is Tn minus 1? Well, Tn minus 1, well, because this is the form of Tn, then Tn minus 1, let me show you in a different, this one. So if this one, wait a minute, okay, so if this is the main recurrence, Tn is equal to 2Tn minus 1 plus 1, then I may ask you, what is Tn minus 1? What is Tn minus 1? Well, because this is just a mathematical function, this is actually quite simple. All you need to do is just replace n, all occurrences of n, by n minus 1. So that means this is an n here, you replace it by n minus 1. So that means this will be equal to 2t, there's n there, and you replace it by n minus 1, n minus 1, and then minus 1 plus 1. And then the final result will be 2Tn minus 2 plus 1. You see? This is simple. So this basically means that we can always perform this substitution again and again. If I ask you what is Tn minus 2, Tn minus 2 again can be described like this: Tn minus 3, Tn minus 4, Tn minus I, for example. What is Tn minus y? Minus I. Tn minus I, Tn minus I. Well, Tn minus I will be, well, replace n here by n minus I. We have here another n, replaces n minus I, so this will be 2t n minus I minus 1 plus 1. So you see, you get the idea right now. So we continue. So that means we replace this Tn minus 1 by this. Yeah. So Tn minus 1, like I showed you previously, this will be equal to 2 Tn minus 2 plus 1. Yeah. Plus 1, don't forget about this one. That's plus 1. This is what we call plug. So you are basically plugging something that we can discover, namely Pn minus 1, Tn minus 1. Yeah, you just plug it. You replaced it by its its form. Yeah, so we plug Tn minus 1 is equal to 2 Tn minus 2 plus 1. You put it, it's basically plugging. And then we perform chugging. What does it mean by chugging? Chugging means simplify. You simplify for this one. How do we simplify this all? Well, look at this. 2 multiplied by 2 is 4 Tn minus 1 plus 2, because this is multiplied by 2 plus 1. So this is basically chugging. Have we seen a pattern? Well, I haven't been able to see the pattern. Well, if I cannot see the pattern yet, I will just perform plug and check again. So right now, our form is 4Tn minus 2 plus 2 plus 1. What is Tn minus 2? Tn minus 2 is 2 times Tn minus 3 plus 1. So I plug it. So you see, I plug this one, and then I chug it. I chug this one. This is 8 times plus 4 plus 2 plus 1. This is 1. Well, let's say that I am not able yet to see the pattern. I perform one more plug. So what is Tn minus 3? Tn minus 3 is equal to 2 Tn minus 4 plus 1. And then I plug it to this one, and then I perform chugging. Chugging will be 8 plus 8 multiplied by 2, 16, plus 8, plus 4, plus 2, plus 1. So you see, we are starting to see a pattern here. What is the pattern? Look at this. What is the pattern? The pattern is, when here is n minus 1, so when we have here n minus 1, we have here 2, and we have here 1. When here we have n minus 2, we have in front 4, and we have here 2 plus 1. When here we have n minus 3, we have in the front 8, and we have 4 plus 2 plus 1. See? Okay, let's continue. When here we have n minus 4, we have 16 at the front, and we have here 8 plus 4 plus 2 plus 1. You see, you already see the pattern right now. So if this is n minus I, if I ask you right now, if this is n minus I, what will be in the front here? Anyone? Anyone? So here, when we have here Tn minus I, what will be at the front here? Well, at the front will be, well, if you see here, n minus 4 is 16. Well, if this is 4, this is 16, then this, it looks like 2 to the power of 4. This one is 2 to the power of 3. This is 2 to the power of 2. This one is 2 to the power of 1. So this is 1, 2, 3, 4. So if this is n minus I expect that in the front of this will be 2 to the power of I. Okay. What about this one? This is 8 plus 4 plus 2 plus 1. Yeah? This is actually, this one, this is equal to 2 to the power of n minus 1 plus 1. Yeah? So well, 2 to the power of n minus 1. So if you see here, 8 plus 4 plus 2 plus 1. This is equal to 15. Yeah, this is equal to 15. So this looks like 2 to the power of 4 minus 1. Let's see. What about this one? This is 7. This looks like 2 to the power of 3 minus 1. What about this one? This is 3. 2 to the power of 2 minus 1. This is 1. 2 to the power of 2 minus 1. So based on this, I have been able to see a pattern right now. And the pattern is this one. So Tn is equal to 2 to the power of k multiplied by Tn minus k. Previously I say I mean this is just equal. Yeah? Plus 2 to the power of k minus 1 plus 2 to the power of k minus 2 and so on until 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. And if you sum this all up, this will be equal to 2 to the power of k, like I said, minus 1. So this is our pattern. This is what I mean by performing again Chug, plug and Chug, plug and Chug, plug and Chug until you see pattern. And this is the pattern. Tn is equal to 2 to the power of k multiplied by Tn minus k plus 2 to the power of k minus 1. Let me return again one slide. 2 to the power of 4 Tn minus 4 plus 2 to the power of 4 minus 1. 2 to the power of 3 Tn minus 3 plus 2 to the power of 3 minus 1. You see, we find the pattern. Okay, so that's it. That's basically the end of the first step. Okay, let's continue. Oh, what do we have to do next? In the second step, it is not enough that we encounter a pattern, we have to verify this pattern. What does it mean by to verify this pattern? Well, it means that you have to prove that the pattern is basically correct. How do we prove this? Well, we can prove this by using induction, but there is another way to do this which is much easier. An easier way to do this, namely, perform once more plug and Chug on the found pattern. So look at the pattern and perform once more plug and Chug. Let me write down the pattern. This is the pattern that we have. The pattern that we determine that we encounter is this one. Tn is equal to 2 to the power of k Tn minus k plus 2 to the power of k minus 1. Perform once more a plug and check on this one. How do we perform plug and check on this one? Look at this. This is Tn minus k. If Tn minus k, how do I do this? Well, this is easy. If Tn minus k, this will be equal to 2 Tn minus k plus 1. Yeah? Yeah? But this will be 2 times Tn minus k plus 1 plus 1. Because the original, we return back again. Let me return again to help you about this. I will just use this again. So here, we already know actually. We already see Tn minus 1. Like the previous one is Tn minus k. What does it mean? This is equal to 2 Tn minus k minus 1 plus 1. And of course, this will also be equal to 2 T, yeah, n minus k plus 1, yeah, and then plus 1. This is equal. Okay, let's return to the slide. So, and then this is plugging, and then you chuck. Yeah, you simplify. You simplify 2 to the power of k multiplied by 2. Well, 2 to the power of k minus plus 1. And then here we have Tn minus k plus 1. Tn minus k plus 1. Okay. And then this 2 to the power of k multiplied by 1. So that means 2 to the power of k plus 2 to the power of k minus 1. Well, 2 to the power of k plus 2 to the power of k is equal to 2 to the power of k twice, namely 2 to the power of k plus 1 minus 1. So this is basically the final result. You see, after we chug it, this is the final result. So let me return again to the previous one. Like I said before, this is actually an induction, but you perform this in a mysterious way, but this is actually an induction. What have we done? What we have done is you perform once more plug and chug and observe right now. Observe, ensure that once you perform plug and chug, then every k becomes k plus 1. This is k, this becomes k plus 1. This is k, becomes k plus 1. This is also k, becomes k plus 1. So, if after you perform plug and chug, every k becomes k plus 1, then this basically means that this is already proved. This is the same as an induction. Okay, let me say it once more. So perform once more plug and chug and look whether every k is transformed into k plus 1. This k becomes k plus 1. This k becomes k plus 1. If this is the case, then you are safe. Everything is okay right now. But if this is not the case, then there must be something wrong with your pattern. Okay? So, the equation on the last line here is exactly the same as this one. The only thing different is k becomes k plus 1. That means they are just the same. Yeah? This is just the same as this one. Because you can substitute k by k plus 1, they remains the same. Okay, so this is basically how to verify the pattern. And then the last step. According to induction, this is enough, basically to show that the formula is applies for all k. Okay, let me continue with the third step. How do we do the third step? Well, once you have the pattern, once you have the formula of the pattern, the only thing that you have to do right now is to use the boundary condition to find the closed form solution. Write down Tn by using previous terms that you know exactly. What do we know? Well, what we know exactly is actually the boundary condition. Yeah, you know the boundary condition. So let me return again to this one, to this pattern. Yeah, this is the pattern that you know. This is the pattern that you know. The result of the pattern is this one. Tn is equal to 2 to the power of k, Tn minus k plus 2 to the power of k minus 1. Let me write this down in Microsoft Excel so that you can see it clearer. So the pattern that you have is this one. Tn is equal to 2 to the power of k, Tn minus k plus 1 plus 2 to the power of k plus 1 minus 1. This is the pattern that you know. Okay? Now, then, what do we do? Well, we don't know anything. The only thing that we know is the boundary condition. What is the boundary condition? The boundary condition is T1 is equal to 1. So because this is the only thing that I know, I will replace this one by this one. So Tn minus k plus 1 here, I will set this equal to T1. So that means Tn minus k plus 1 equal to T1. Well, what does it mean? Well, this simply means that n minus k plus 1 will be equal to 1. You see? So, if this is it, what do I do right now? Well, find the form of, find the form of n. So this is basically what I do in the slide. Let me return again to the slide. Okay, let me return again to the slide. The slide says that take k is equal to n minus 1. If you take k is equal to minus 1, then we can basically express Tn right now by Tn minus k is equal to Tn minus n minus 1, which is equal to 1. You know what is the value of T1. Yeah? So let me return again to here. This is Tn, which is the result 2 to the power of k, Tn minus k is equal to 2 to the power of k minus 1. Okay, I think I just made a mistake in the Excel. Let me return again here. You don't have to use k plus minus 1 here. You just use k okay. So okay, you look at that. Yeah. So this one will be n minus k. That means that n minus k is equal to 1. Yeah. So if the only thing that I know is T1 is equal to 1. So I have here Tn minus k. I will set this equal to T1. So Tn minus k is equal to T1. So something that I know, I fix it by something that I know. Yeah. So I fix this. But what is the consequence of this? The consequence of this will be n minus k, which will be equal to 1. Well, if this is the case, that k will be equal to n minus 1. So that's it. Yeah. Once you know k is equal to n minus 1, you can basically replace all the occurrence of k here by n minus 1, and you will basically find a solution. So how do we do that? Well, let's say this will be equal to Tn is equal to 2 to the power of k. K is equal to n minus 1. So n minus 1. Yeah? Oh, what about Tn minus k? Well, Tn minus k is already equal to T1. So this we just right away is equal to 1 plus 2 to the power of k. 2 to the power of k. Okay, 2 to the power of k. K is equal to n minus 1. 2 to the power of n minus 1. And then what is left? Minus 1. Okay, so what else? Well, here is 2 to the power of n. T1 here equal to 1. So this basically becomes 2 to the power of n minus 1. Here again also 2 to the power of n minus 1, because there are twice 2 to the power of n minus 1. This will become 2 to the power of n. And then it's still left here minus 1. So that's it. Yeah, let me return again to our slide. That's it. Without basically guessing, we have just found our solution. And this is the solution of the recurrence. Tn is equal to 2 to the power of n minus 1. And that's it. Okay? Now, let me continue with one more example before we have a short break. And then we can continue with linear recurrence. Yeah? And I will go a little bit faster here. Yeah? And this is called merge sort. I will not describe to you what is merge sort. You can read it yourself. I will go right away to the recurrence. The recurrence of merge sort is one. This is the recurrence. T1 is equal to 0. Tn is equal to 2. Tn divided by 2. Look at this. This is divided by 2. So if the previous one is n, the second one is n divided by 2 plus n minus 1. And we are going to solve this recurrence. Okay? Now, how do we solve this? Well, you think that, well, let's try to use guess and verify. If you use guess and verify, you will not be able to do anything, because if you try to guess, you can try a couple of values, then this is the result. T0, T1 is equal to 0. T2 is 2. T1, because this is 2 divided by 2, plus 2 minus 1 becomes 1. What about T3? Well, there is no T3, because T3 will be 2 T3 divided by 2, which is not basically an integer, and we cannot use it. Well, we can continue with T4. This is T4. T4 is equal to 5. T8 is equal to 17. T16 is equal to 49, and so forth. But it is not easy basically to see from this sequence what is the, it is not easy basically to guess. You see? So what do we do if you cannot use the guess and verify? You can try to use plug and chug. Let's try to use plug and chug. Okay. Again, don't be afraid. If there are a lot of equations here, you can actually we can do this. Yeah. So this is the recurrence. The recurrence is the main recurrence is Tn is equal to 2 Tn divided by 2. So basically the parameters here, n divided by 2 plus n minus 1. Okay. If I ask you right now, what is Tn divided by 2? Well, Tn divided by 2, you can just basically replace every occurrence of n here by n divided by 2. So that means Tn divided by 2 will be 2 times T n divided by 2 plus n here. Well, the n here will be n divided by 2 because every n, change it by n divided by 2 minus 1. So this is it. This is basically what we mean by 2tn divided by 2 becomes 2tn divided by 4 plus n divided by 2 minus 1. So you plug it. You plug it here. You replace tn divided by 2 by 2 tn divided by 4 plus n divided by 2 minus 1. So you have this one. This is basically what we mean by plugging. What do we do next? Simplify, chug it. So if you simplify this, this becomes 2 multiplied by 2, 4 tn divided by 4. Well, I'm sorry about this. This is supposed to be n divided by 4. Yeah. And then, what else do we need? Here, 2 times n divided by 2. Yeah. 2 times n divided by 2. Look at this. 2 times n divided by 2. Well, this is n minus 2. This is minus 2 here. And then plus n minus 1. Okay. Let's continue. Now, what about tn divided by 4? We perform again a plug. Tn divided by 4 is equal to 2 times tn divided by 8 plus n divided by 4 minus 1. So this is basically our plugging. Yeah, this is our plugging. So, and then we check 8 times tn divided by 8 multiplied by 4 multiplied by n divided by 4. How many is that? Well, 4 divided by n divided by 4 is n. N, but then there is here 4 multiplied by minus 1, n minus 4. You see? N minus 2 plus n minus 1. Again, let us say that we don't know it yet. We can see the pattern. We haven't been able to see the pattern. What do? We perform one more chugging, one more plug and chug. Tn minus 8. What is Tn minus 8? This is 2 times Tn minus 16 plus n divided by 8 minus 1. So this is it. Yeah? So you plug it there. And then once you plug it, you perform chugging. 8 multiplied by 2, 16. Tn divided by 16. This is 8 multiplied by n divided by 8. N minus 8, n minus 8 plus n minus 4 plus n minus 2 plus n minus 1. So you see here. Yeah? So we are going to see, have we been able to look at the pattern? I mean, how do we look at the pattern right now? I mean, what is the pattern? What is the pattern? Well, let's see. This is the first step. And in the first step, this is n divided by 2. The second step, n divided by 4. The third step, n divided by 8. The fourth step, n divided by 16. You see? Now, n divided by 6, n divided by 8 here, 8. N divided by 4, 4. N divided by 2 multiplied by 2. N divided by 16, 16. So, what is here? 16. It looks like 2 to the power of k. If, yeah, in the next one, in the first step here, this is basically when k is equal to 1, so 2 to the power of k, 2 to the power of 1. So it looks like 2 to the power of k, 2 to the power of 1, multiplied by t, n divided by 2 to the power of 1 also. Okay, what about this one? This one, 2 to the power of 4, multiplied by t, n divided by 2 to the power of 4. You see, so this one is solved. We see the pattern right now. What about this one? It's actually not really difficult. Here we have here, how many n's do we have? N, 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 4n. Well, when this is 2 to the power of 4, this, how many n's do we have? 4n. Okay, that's it. What about here minus minus 4, minus 8, minus 4, minus 2, minus 1. We have already seen this before. If this is 16, then this is 8 minus 4 minus 2 minus 1. This is 15. So 2 to the power of 4 minus 1. When this is 8, this is 4, 2, 1. 4 to 1 is 7. So 2 to the power of 3 minus 1. So you see, we are able right now to find the pattern. And this is the pattern. Tn is equal to 2 to the power of k, Tn divided by 2 to the power of k, plus Kn minus 2 to the power of k plus 1. What about this one? What does it mean by minus 2 to the power of k minus 1? Because here it is minus. You see? Minus 8, minus 4, minus 2, minus 1. So if you complete this all, this will be minus 2 to the power of k minus 1. Yeah? So minus 2 to the power of k. Of course, this is not minus 1 because this is a minus there plus 1. Okay, so this is basically the second step. Now let's see the second step. Yeah, the second step is basically to verify the pattern that we have. How do we verify it? Perform once more plug and chug. This is the original pattern, and we are performing once more plug and chug. What is once more plug and chug? 2 to the power of n, 2n divided by, sorry, Tn divided by 2 to the power of k. What is the formula for this one? The formula is 2 times Tn divided by 2 to the power of k plus 1 plus n divided by 2 to the power of k. Try it yourself. Minus 1. How do I know this? Well, by using the main recurrence again. This is basically plugging. And you perform one more chugging. 2 to the power of k multiplied by 2. 2 to the power of k plus 1. This one, T n divided by 2 to the power of k plus 1. So this is okay. What about this one? There are 2 to the power of k here, multiplied by n divided by 2 to the power of k. So that means 2 to the power of k is just disappear, becoming n. Yeah? So, but here we have here k times n. Here another n, so this must be k plus 1 multiplied by n. Okay. 2 to the power of k here minus the multiplied by minus 1. Multiplied by minus 1 is equal to 2 to the power of k, but there is another 2 to the power of k here. So the summation of this one is minus 2 to the power of k plus 1. And there is another plus 1 here. So this is the final result. And if you see, once we perform plug and chug, what we have to do, the final result is just transforming every k here becomes k plus 1. K plus 1, k plus 1, k plus 1, k plus 1. So this is correct. Okay? Okay, let me continue then. The final step. What is the final step? The final step is to use the boundary condition. What is the boundary condition? The boundary condition is this one. This is the only thing that we know. T1 is equal to 1. We are going to use that basically by looking at this formula. Look at this. This is basically the pattern that we obtain. We obtain Tn is equal to 2 to the power of k, Tn divided by 2 to the power of k plus Kn minus 2 to the power of k plus 1. What do I do right now? The only thing that I know is equal to T1 is equal to 0. I will set this one equal to T1. Well, that means if this Tn divided by n to the power of k is equal to T1, then the result will be yeah. So our formula previously is this one, T n divided by 2 to the power of k. I will set this equal to T1. What is the consequence of this one? The consequence of this one is n divided by 2 to the power of k will be equal to 1. Okay, now I'm going to find k. Look at this. I'm going to find k. Well, this is n divided by 2 to the power of k is equal to 1. So this basically means that n is equal to 2 to the power of k, just multiply it to the other side, 2 to the power of k. Okay? So what is k then? K is equal to, well, logarithm of n. What is the basis of the logarithm? Well, the basis is equal to 2. Yeah? So this is k is equal to the logarithm of n with the basis of the logarithm is equal to 2. Okay, let me return to the slide. Oh, that means we said k is equal to the logarithm of n. When k is equal to the logarithm of n, then tn divided by 2 to the power of k is equal to t1. What is this? It's equal to 0. So we just put it to the pattern that we know. 2 to the power of k multiplied by t n divided by 2 to the power of k plus tn minus 2 to the power of k plus 1. We know k, so replace all of the k here by what we know. Because k is equal to logarithm of n, this is 2 to the power of logarithm of n. Yeah? And then, what else? Well, this is multiplied by this one. Yeah? Multiplied by t1. Yeah? Multiplied by t1. This is basically what I mean. Yeah? And then here there is kn. K is logarithm of n multiplied by n. And then here k, 2 to the power of like n plus 1. What about here? Well, tn divided by 2 to the power of logarithm, the logarithm of n. This is easy because we already know that previously 2 tn divided by 2 to the power of k is equal to t1. What is t1? T1 is equal to 0, so this does not mean anything. This becomes 0. So the whole thing here becomes 0. Okay, what is left? N multiplied by logarithm of n, n multiplied by logarithm of n, minus 2 to the power of logarithm of n. What is 2 to the power of logarithm of n? 2 to the power of logarithm of n is equal to n. Minus n plus 1. So the final result is equal to n logarithm of n minus n plus 1. Okay? So I think that's it. So that's basically, I have already shown you 2 examples right now how to use plug and chug. So I will give you, well, let's have a rest around, I don't know, three minutes, and then we will continue our lecture afterwards. If you have any question about this and something that you basically miss, something like that, ask me by sound, or you can ask me also from the chat. Okay.